And you know there's that actual literature bar on the Rubik. I've got like the not top 100, but middle.
We will end up getting chocolate.
I'm just assuming because there was nothing bad about my.
Is it? It's true.
Makes sense.
Engineering, 19.
Sounds changed, isn't it?
So,
Hammer?
you're basing it off.
And I didn't know. Right?
I'm doing now. Better.
Good morning, everyone.
Yeah, they're like, oh, we need that last.
Nice to see you again after a long.
Okay, cool. So I went and saw it and I thought,
So,
Yeah.
me? Nobody wants to see me. Yeah. Next week, just a brief update about what place we are standing at. Next week is the last week of the semester, of course, and you have a coursework to submit and write. And in the next semester, we have lots of other things to do. But next week, Julia Stevens from Constructionarium, she's coming here. She will deliver a talk. It's, I don't know, from when until 11:30, I think. So we all go to that session. It will get the first half an hour of this session. So after that, we come here and we continue the concrete together, all right? I will send an email to everyone just to confirm the the exact time and date. But so practically next week we will miss half an hour. That's fine. We will compensate in other forms of teaching during the different weeks by videos and Q&A sessions.
Will you be the
Yes, I will come as well. So. Okay. I mean, after that, we want to go to the lab? That session? You told me.
Yes, I remember.
Yeah, I will participate as well, and you will participate. Yeah, we will go there. After it finishes, we will get 5-10 minutes break, and we'll come. All right? Good. So today, I want to continue my discussion about beams, but we so far understood that how to design beams, sometimes single reinforcement, sometimes double reinforcement if we have a lot of external forces, and how to design it for shear reinforcement. And also we talked about slab design, which is really the same as beam. It's a long, very long beam, but it's called a slab. So it's practically beam, and all the concepts in the beam design is valid for the slab as well. But still, these are the design concepts for the beam and slab. Still, there are a few things to cover about the beams and a slab. When I say beam, slab is beam, so both of them. There are a few things to cover about beams, which one of them is the deformation, and a few more things. There are side things that we need to cover. For example, the arrangement of the reinforcement, how much distance we need at least between the reinforcement to be sure that the concrete will pour and the aggregate will not stuck between the reinforcement, stuff like that. So 1, 2, or 3 sessions we will talk about these. The first one is the deflection. Whatever you designed was about forces, wasn't it? You had a force, you were designing for force. It's called force-based design. So everything about this design was about forces, but we didn't have any clue about the deformation. What's the deformation? If you do all the design for your beams and at the end, or a slab, you will see some sort of this deflection, what you feel. It's very scary, isn't it? Although if this be able to carry the applied loads, but this sort of deflection is very visible with eyes. It's very scary for people. So nobody wants to see this, neither many other cases that when you take some photo, you need to reference it. All right. Yesterday I had, and the day before I had presentations from master's students at the university. It was a part of one of the modules, not my module, somebody else, but they needed help to. There are too many, so none of them. They are master's students. You are undergraduate students. I don't know why, but in this university, undergraduate students do better than master's students. I don't know why, in every aspect. None of them has cited the pictures they provided in the presentation. If you do not do that, it's called plagiarism. Slight version of plagiarism. So it's like the plagiarism, it's in layman language, means stealing somebody's some property from somebody. If somebody has taken a photo, put it in book, paper, website, internet, whatever, wherever, if you take that, copy it, paste it in your report without citing to it, it's a sort of stealing that material. It is a digital material, but it doesn't make sense if you just go break the door and steal something physical from their home. So it means that you need to comply with the referencing. I'm pretty sure you know, I'm just mentioning again that it's a good practice to reference. It's not a good practice, it's essential practice to make a reference when you take something from somewhere in your report, in your presentation, wherever you use it. Another thing is that from this perspective, you can see this bridge. Can you see the deflection? Right? The deflection is visible. And this occurs in concrete structures because of two reasons, which are common in concrete elements everywhere in all the cases. The concrete elements are prone to two effects, shrinkage and creep. Who knows what's shrinkage?
Get smaller.
Yeah. When you mix concrete, you have aggregate, water, and cement, right? And sometimes some additives. Anyway, when you pour the concrete, it will get dry. Okay, you need to cure it, you need to moisturize it, but anyway, the inherent water will be vaporized. And because of the loss of water, the volume will be smaller. So this means shrinkage. What's creep?
Creep is like a failure.
No, that's fatigue.
Creep is like bending of your laptop because it keeps your hand over the same place for like ages.
Laptop?
Like suppose you keep a hand on your laptop on specific place for a long time and it gets a dent forever. That makes sense.
No. I didn't get you. Put your hand on laptop, what happens?
Sit on a place for long, like forever on this, and place your hand on the desk on the same place. It dents up after some years or something.
It's like slow failure.
Like slow failure, but not failure exactly. Like
Deformation of a structure under constant load.
Under
Constant load.
and over time. That's the definition of creep. Did you Google it? Got you. It's not the case in steel structures, but in concrete structures, when you have a beam or a slab, okay, after 28 days, it gets the strengths that it should have. But yeah.
And does it whilst it's hardening? Normally, it's what it shrinks whilst hardening. So they normally.
What's the
So
question?
whilst hardening,
Okay.
it shrinks. Is that
It
correct?
shrinks, yes.
Yeah.
But it's almost about, for example, 28 days, 1 month. After 1 month, exactly 28 days, you get the design strengths that you aim to.
Is that why when you typically dry pack the areas, or you fill in an area which hasn't been cast by the concrete, you wait 2 days for it to shrink or?
No, you need to cure it for 20 days at least.
Yeah.
All right. Cure means that you need to make the atmosphere, the surrounding area, moisturize it to help, because the water, the inherent water the concrete needs that water. If it gets dry, it will not get to the maximum strength that it should get. Right?
This is my final question, sorry.
So it's only about 28 days, okay? But creep isn't about 28 days, it's about years. Okay, after 1, 2, 3 years, under constant load, it will deform more than the initial deformation. For example, after 28 days, it has some deformation because you start loading the structure, right? If it's a building or a bridge, okay, it has a deformation. But after 1, 2, 3 years, over time, the deformation will be increased. And this increase in the deformation over a long time is called creep. And it's particularly for concrete elements, not for steel structures. So the calculation of this deformation is not very easy because concrete is a mixture of steel reinforcement and concrete, and if you want to really calculate the precise deformation, you need to rely on very complicated theories. There are some, but as you know, the code, including Eurocode, aims to simplify everything for us, to provide some simplification versions to be able to calculate the deformations and provide you with some thresholds. Okay, if the deformation is less than this threshold, you're fine. If it's not, you're not fine. So this is what the Eurocode does for us, right? So this is what we want to do today, that what is the acceptable deformation for a beam or a slab? Any question? So we are in section 6.7 of the book. I don't want to go for some of the details. I want to just transfer the idea of how it works and how Eurocode deals with it. So because of creep, because of shrinkage, because of varying modular of elasticity, because of the percentage of both tension and compression reinforcement we have in the section, calculation of the deformation is not very straightforward. It's very complex to calculate the deformation. But Eurocode clause 7.4 aims to give you some insight to the methods that are simple to be used with some factors, formulas, to calculate the deformations and see if your beam is okay or not. Here it is a simple beam on 2 simple supports with lengths L. The section is B and H, cross section. And for this simple beam from structure analysis, you know that the deformation is this one. Sorry, this is the maximum bending moment at the middle of the beam here. At the middle of the beam is the maximum bending moment. The maximum deformation is at the middle of the beam as well. If you calculate the deformation will be this one. This can be done by structure analysis concepts or with those methods that we had in engineering analysis that you were not done. So in structure analysis, you have several methods you can calculate the deformation of this beam, this delta. And for uniformly distributed load, it's like this. And it's just elaborating a little bit with the formula that can be finally interpreted like this. The multiplication of these two factors. This is FCE, is modulo of elasticity. FC is the strength of concrete. This is important that we have L over H here. It means that the delta, the deformation, the maximum deformation, relates to the ratio of L over H. And it makes sense physically, because the longer beam you have, the more deformation you will have, right? L over H. L is the length of the beam, right? The longer beam you have, the more deflection you will have, right? If H increases, what happens? The more H you will have, the less delta you will have, right? It will be more stiff, because when you have H, H contributes to I is the second moment of inertia, 1 over 12B H3. So it's cubic H, so it's very important. H very significantly contribute to the deformation. So the more H you have, the less delta you will get, right? It makes sense from the point of physical sense, right? So the delta is a factor of L over H. So the Eurocode tries to use this concept to give you some insights, some formulas, some methods, approaches, you will work with the L over H, the length of the beam over the height of the section. And if we can be able to restrict this ratio to some certain threshold, we will be fine. That's the main idea. Any question? No? Yes, we are recording. Let me just check again. Should be somewhere. Yeah, we are recording. So, Eurocode says, okay, we talked about L over H, but it better makes sense if we say L effective over D instead of H. Because D is effective depth minus cover, something like that, right? D is more important to the design. When we want to design the beam, we only work with D, not H, because that 5 centimeter at the bottom doesn't work at all in anything. So maybe it's better to work with D instead of H and L effective instead of L, because in most cases you have a beam on a support, so this free length is called L effective, although the ax to ax is L. So those parts sitting on the support really do not contribute to the deformation, because when it's like this, the deformation is really in this part. This is in this. When it's when it sits on two columns, for example, the deformation is here, not into the column, right? So the free length of the beam is called L effective. So it's better to work with the effective length over D instead of L over H, right? So in that case, we will work with L effective over D. This is our key parameter to monitor the deformation. And you saw that the deformation is a function of this, not equal to this. We had some other parameters, right? So the Eurocode needs to define something to multiply to this and say, okay, this is the deformation. For that purpose, first of all, we work with L. We will have, don't worry about these, but we will have some correction factors in the formula just to multiply to these. One of them is F1, F2, and F3. I will tell you what are they, but they are the correction factors in the formula will be multiplied to correct the formula. You know, I said in the previous slide, I said the deformation is a function of L over H. So we have something at the back of the formula. And also this is only for a simple beam. If it's not a simple beam, if the both ends are fixed, what happens? So we have different sort of beams and so different conditions. In those cases, we need a more generalized form of formulation to be able to work with. These are those formulations of Eurocode. These are two formulations of Eurocode to check the deformation for a beam or a slab. Don't worry about it. It's a very big one. It's not very complicated. We have a couple of parameters and we will check each by each, all right? First of all, we need to see which one is our case, if we are here or here. Rho and rho 0. Rho is the required tension reinforcement ratio at midspan to resist the moment due to the design loads at support for cantilevers. Because you know, if you have cantilever, the maximum is at the support. If you have a regular beam on two supports, the maximum is in the middle. So it means that you need to work with the maximum. Where is the critical section? If it's a beam on two supports, it's a middle. If it's a cantilever, it's at the support. All right? So only the tension reinforcement, no compression, because we have this one for compression. Okay? Rho always stands for the reinforcement ratio. It's dimensionless. It means that rho is AS, the area of steel, over BH, the total area of your cross section, right? So what is rho 0? Rho 0 is the reference reinforcement ratio, which is this simple formula, 10 powered minus 3 square root of FCK. FCK, you know, when you know the concrete grade, you know the FCK. If it's the first number, C3035, 30 megapascal is FCK, isn't it? So we can simply calculate rho and rho 0, and we can figure out which formula we are allowed to use. But let's take a look at the other parameters. Any of these formulas, we need rho 0, whatever we have. Here we have rho prime. FCK. What else?
Okay.
Yeah, F1, F2, F3, and K. Right? If we have these parameters, just put them there and just, it should be less than this. The Eurocode, it says equal, means that if the L over D is less or equal than this, you are fine. If it's not, you're not fine. This is not something, it shouldn't be. It's the problem of Eurocode. You should say less or equal, not equal. So we calculate this as the criteria for the deformation, and we have our beam. We know the lengths and the H and the D, the effective depth, and if it's less than this value, we are fine. If it's not, we are not fine. What does it mean if we are not fine? You should, what you should do? You should
Change the section.
Yeah, you should change the section to make it more stiff. You should increase the stiffness to decrease the deformation, right? For example, if you can change the breadth of your section, but it's not as effective as if you change the height of your section, because as you know, the second moment of inertia is 1/12 BH cubic. So B is not a, it is a player, but H is a strong player. So H, if you a little bit increase H, it will have significant influence rather than increasing B. All right? So F1, 2, 3 are correction factors. I will tell you how they will be calculated. And K is another parameter. I will tell you how to get it. It's here, K. It's a factor to take into account different structural systems. It will be given in table, this national annex or this one in the Eurocode. I will provide them in the next slide. So all together we have 8 parameters to calculate this formula. All right? So in the next 2 slides, I've provided the K factor. This is the next 2 slides means this is coming from Eurocode. But when you go to the Eurocode, it says if you have the national annex, you should go to your national annex. All right? The UK national annex gives this like this table. All right? This is from national annex. And if you compare these values with these values, they are identical. They are the same. It means that in this section, Eurocode and national annex are the same. All right, but you can these values are the rough values for these cases. For example, simply supported beam 1 or 2-way, spanning simply supported slabs. But from this table, I need K only, because this is something that I want to calculate based on that formula for my specific case. But from this one, you can take your K value, which is either 1, 1.3, 1.5, based on if you have cantilever, it's 0.4. Based on different systems, you have different K. It's a parameter, it's a correction parameter, okay? Still, you need F1, F2, and F3. And don't worry about them. I will tell you what they are in an example in next slide. Not next slide. This is a part of Eurocode as well. Just not to forget, this is F1. Again, this is a problem of Eurocode. Again, this is a problem of Eurocode. Should be mentioned. This is F1, which is this one, F1. This is the formula for F1. And One of them is this is talking about F2, and this is talking about F3. We will see, I will get back to this when I'm solving the problem, okay? Most of the time F2 and F3 are 1. And F1 is something like between 1 and 1.4. Something like that. So they're not big numbers, all right? I will get back to this when I'm solving the example. Do you want a break before we start example?
Yes, please.
Because you just came from another session. Yes. Just get some water and stretch your legs to start the.
Delicious, bro. I've never had meat. Did. Never had meat in my life.
Didn't it mean boss or I thought it meant teacher.
It was just as good. I was surprised.
Yeah, he doesn't mind. It's neat.
Do you have a presentation today?
You got trim, no?
What time
It's
is
just
yours?
neat. It's just my face just looks angry.
With Nick.
Gangster.
Mine's at 4, but I'm next to Amy.
Gangster's Gangster. What, did I join them up?
I am, but the rest of the group is a bit weird.
There's no gangster.
Hamza, look at him with the jacket and
Why
the
does he think I'm a gangster? Like, I don't look like a gangster.
I mean, say, be honest.
Have you ever seen Prison Break?
Yeah, I see
Have
prison.
you seen Prison Break?
Yeah, see? There you go. I look smart.
Yeah, you look smart.
You look smart, but you look like gangster.
It's fine. It's fine. Like, this, I sort of shit quickly.
Yash is the gangster.
Yeah, Yash.
Yash is the real gangster.
Yeah, it's not
Let's go out.
Yeah, I'm coming.
0%.
That's good.
Should I send that?
I think that copy of Sam's
Which part is off? First of all, check introductions.
Told you, it's alright, but
Sometimes
It needs more.
usually the module of less specific.
Introduction for one page.
Everything written, meter,
all of this.
so
This needs to be
compatible with each other.
30.
Otherwise, if it doesn't work, you
That's what I'm saying.
up
to it.
okay, like example, and you will find it.
Yeah,
Otherwise, if
it's basically just us three.
you do that,
It's basically
write it very tidy on a piece of paper and send it over to
the
me.
same thing, and me or Sama.
There's no way.
Timmy.
Usually, if you write it on a piece of paper and the same thing, follow the steps, usually you get the error.
A read call.
If you couldn't, just let me know. Okay?
Fuck that.
Group design project.
Get marked as AST.
Don't use GPT for it, okay?
What are you using it for?
For the group design.
Yes, sure. Who needs GPT for design? Come on, man.
You need to use GPT for everything.
No, some of it I did by myself.
No, I'm saying the group design project. How's this one?
How I mentioned.
I did it. It's not too bad, or Excel. And
I mean, I think not more than 6 or 8.
I don't know. It's not.
You all in the Excel.
Yeah, but basically on the first two lectures, there needs to be, I think, on thingy, bigger than smaller in your numbers.
Put our
And
number
and
in.
obviously discussion is your part. When ChatGPT, I was trying to do this. I was trying to which thing in lecture, I'll double check. The third.
So we're the.
So then I checked in the lecture. Checked on Google like what's the minimum. I need to double check. I haven't gotten that far. I haven't got to, yeah. So I tried to.
1 and 2 is from 5. It's 2 lectures
Instead of 3.
Yeah, increase the reinforcement.
So I got
Then
then I was doing
he
the
uploaded a lecture.
still you would
I think it might be that. I don't know.
Y value which is supposed to be bigger than the f over t value.
Yeah.
Mine was Can you figure out the problem?
Your strain was not
For
yield.
me, it's quicker as well. Yeah. You can do the hand calculations.
Do you know how to use Excel?
So just
No, it doesn't make sense because if it
We had to
doesn't
use it
yield,
for
which means that your x over d is more than 0.6.
Did you figure out the problem?
Yeah.
Just put my.
I'm just gonna try and
When
try to redo it.
Change everything.
if x over d is more than.
If I can do it by hand, you can. If I find a mistake,
Means that
you do it by hand.
No.
It doesn't yield.
Have, man.
That's why we reduce this
Is that these two values?
Have a look.
yield.
Come on.
If this is less than
Is that these
45%,
two values? The C are
it
built
means
up.
that you should be sure that the steel
What
is
did bit off
yield.
as a radio?
What did I do?
Maybe I'll just
Probably I've done some mistakes. Yeah.
I don't know.
If it's less than 45%, you're still.
No, that's right. What's up, then?
double checking.
When those C's from, I started. I've done singly, but not doubly. I don't know. It just seems off.
Huh? No.
I just got how.
No way, bro. Leona's done it, bro. It looks like his floor plan.
Oh,
Yeah. Yeah, yeah. I thought that was your floor plan.
Minesweeper, bro.
So,
Too busy.
I know. I probably need to recheck.
With this research alignment.
But personally, yeah, I'm different. It takes me.
That's this one.
I don't just understand it. Just quick out.
We haven't even done.
It's like you're.
The soil thingy that Panos needs to do.
I want to do that this weekend.
Panos is doing it, no?
Yeah.
Panos is doing it for us. And
No,
uploading.
you know what he showed us, like a little annex thing.
And that was this one.
Annex, that's it.
Oh shit, for the presentation. I'm coming to it.
I'm coming into it as well. If you're in the same room as
They're upstairs and Hamza's downstairs.
Oh, you're watching Hamza's ones.
yeah, you came to watch ours.
Oh, yeah.
We're like just purely intimidation.
Quite fun.
Oh, you know what's the thing is Amy as well, so.
Yeah, I heard she's hard. No, she's hard. She's
Really?
worth.
I also wondered.
But Nick,
Apparently,
It was
us
good.
getting Nick Green was
Nights and then.
Nick,
People had it
formal and
like written down on like notes. I memorized it. But
anyone that has a problem with, you know what I mean?
you're on today as well.
What would you rate it as a graded perspective?
Who's your one with? Nick or
I said that to me.
Till 6.
yeah, Joyce?
Really like formal.
What time?
We weren't dressed.
Our one was good, wasn't it? Our one was
We got
good.
dressed formal and now I think we
It's
should.
fine. No, I don't think it matters.
It looks nice though. You see the engine
Mechanicals, yeah, they weren't very good though. They weren't very
Do
good.
you know
The
that?
last group wasn't good.
Yeah.
So,
Did you watch it as well?
basically, I heard it and I ducked out.
They were rubbish. They were absolutely rubbish.
But the thing is, it was Nick, so he's blessed with it.
But they did it about hotels.
Yeah. I don't think the assignment didn't say specifically.
Engineering, I thought engineering practices.
No.
They were rubbish. They were really bad. They didn't even compare it to other companies, and they didn't say the disadvantages.
Again, they got Nick, so it was Amy should have looked into them. Yeah, like they build what's it called? Bus lot.
Is it?
Yeah. Apparently it's too broad. 0.5.
Too broad.
Yeah.
Which one's Amy? The
The
old
presentation covered like too much.
I remember her in
What company?
Deborah's Sims last year, or what you guys had for
What
Deborah.
company did you lot do it on?
MCM. It's like a
MCM. Banking, isn't it?
No. MCM.
I say that we got 85% in our presentation.
Florida University. There was like a bridge collapse.
Yeah.
So it was the company that
They have it in Las Vegas. Yeah, they got it in Las Vegas.
It was in Florida, so Florida University, the bridge collapsed, and we done it on a company on that. Turns out they didn't update their policy after the collapse, so.
Bring my guns out.
Yeah, I think MCM does do Las Vegas. Just trying to.
Again? So it's called Magnum Construction Management.
Magnum.
Yeah, they do Las Vegas.
You know, whenever it says D in it, that's.
I mean, they're up, like they're doing well now. They won an award.
Magnum. Was it Magnum?
Construction Management.
That whole thing is. Yeah. That's it.
I tell you what I'll probably come do. I'll come half day on Sunday. If we're not coming.
You guys got a script, so you're just gonna read, yeah?
Try and not use a script, man.
We had scripts.
We had script. We did. I don't think anyone used.
Yeah, people kind of used it. Ishmael used it.
Right, be honest, did you memorize it? Because Yon was fluid.
I memorized it.
He done
Memorized
it 2 nights before.
Fuck that.
It was good, wasn't it?
Bro, but you should have heard me before.
I think I should have done it for a bit longer.
How long was our presentation for? How long did we take?
It must have been about 12 to 14 minutes.
It wasn't that long, was it?
got the introduction.
You got, on average, you got to speak 2 minutes each person.
Yeah, but we've done a thingy count on there.
That one is.
The thing is, a lot of people, with Nick, he doesn't mind it going over. I've seen it, he doesn't mind it going over.
Oh, sure.
Either way, he doesn't mind. I don't see him complaining.
So we're quite blessed. Hopefully he blesses us with a grade as well.
Like that.
Oh, she measures time. Where's Aliona?
I'm gonna say to him.
Should be coming. Wait, did you have it last time or something?
No, I just heard about it.
Oh, you heard
Serious presentation.
Everyone heard about it. Like, we were shook.
She was shook. It's not my first language.
That's me, man.
No, I heard about it.
And you know what? She's got the most to talk about it now.
Really? She put pressure on herself.
Yeah?
She put Shemi on it. Shemi's a good public speaker.
Yeah, I still remember, yeah, in the Constitutionarium. Those reports were good.
Out of 10?
Daniel,
Out of 100.
what you did, intro?
I didn't
Fusion. Comparison. Yeah, that's a big part. That's what Umar did. That's a big part, you know. That's like 25%. Have you done advanced?
Oh,
You got 2 minutes on that slide.
Oh, you didn't know that?
Don't miss out any 3 minutes on it. No, anything. If you miss anything, you take out anything from respect.
And you know what? We other health and safety.
Good evening,
stakeholders. That's it.
We tried to emphasize on the design.
Sure, I said stakeholders.
Health and safety. Rio said.
Trying to
let me move some of them in, so like,
showed us it. So much. Literally, will help us with the report next week.
Is that what you based?
We already got the
Is that what you based it on?
based on
Oh my no.
basically what they had the axe.
The stairs.
One of the main, like, what
Me.
that even though there was like 8 devs.
Main topic.
But the main topic was safety.
Are we gonna just change?
And then the health and safety check.
Mezzanine one is beautiful. It's fine with the mezzanine.
A lot of what comparisons are you talking about?
We went through a fucking 70-page.
Just do one straight and one like.
Yeah.
Use about
They know.
Amy downstairs or Amy upstairs?
You might switch just.
No, I asked Nick. He goes, yes. And eventually, fuck up.
He was like,
Looking at me.
Read it.
I'll fuck up somewhere like.
Shall we continue?
And then
The first example, 613, says, consider a rectangular concrete beam like 250 millimeter by 475, and it's a simple supported beam which the length is 6 meter. And using the data given below, the concrete strengths, this is FCK 40, the characteristic steel strengths of steel FYK, and design ultimate bending moment at mid-span is this one, and distance to center of main steel is 50 millimeters, so it makes your life easier. You can straightforward get the effective depth because it says not the cover only, the cover plus half of the reinforcement diameter.
Megapascal, sorry.
40 megapascal, yes. The aim is, okay, you can design it, we will do it, but you can design it, get some reinforcement, of course. The aim is to see if the deflection is okay or not, as well, all right? So this part, until here, is the repetition of what we already know, right? Because it's the design of this beam for this 150 kilonewton meter. Because if you remember from design of beam reinforced concrete beams, first of all we calculate K. We have 150 kilonewton meter divided by this, we will get this one. We have K prime from that table, if you remember, which in the case of Norrie distribution, K prime is 0.168. And the main idea was compare your K with K prime to see if your K is less than K prime, which is the case now. You go for single reinforcement. And if it's not, your K is more than K prime, you have to go for double reinforcement, right? This was the main idea of designing a reinforced concrete beam or slab.
Say that again, please.
If we calculate K for our case, which depends on the external force and BD and FCK, which is this number. If this is less than this one, you need single reinforcement. If this is more than this one, which is not now, you need to go for double reinforcement. Double means bottom reinforcement and top reinforcement, tension and compression, right? And for each of those cases, we had different formulas. This was the main topic we talked about from the beginning of this semester until you went to the construction area, right? We had a lot of examples of singly and doubly, right? So this was the criteria we distinguish if we need to go for single reinforcement or double reinforcement.
Yeah, at the beginning.
Pardon me?
You do that at the beginning.
Yeah.
The MED is given. Question.
Yeah, it's here, 150 kilonewton meter. That's the external force coming from ETAPS, okay? So This part is, I don't go through this because it's the repetition of what we had a lot of these things before. If you do not remember, just go to the previous sessions. Recordings are there and examples are there. These are what we do for singularly reinforced structures. And at the end, I will come up with this AS 883 square millimeter. I need this amount of reinforcement at the bottom of my section as the tension reinforcement, right? So to comply with that, if I use 3 reinforcement number 20, it will give me 943. It's always the case because I need to get a couple of reinforcements, so the reinforcement I will get is a little bit more than I really need. Okay, this is important here. These 2 numbers are important here. So until here, it's just the design of the beam for singly reinforced case. And now this part is new. This part is from clause 742 of the Eurocode, which talks about deformations.
You want your 942 to be larger than the 88.
Yeah.
You want it to be a significant amount, or like 100 is good.
As much as closer, better.
As close as possible.
As close as possible.
It
Because,
saves material.
yeah, if you use, for example, I don't know, number 18,
Yeah, 3H.
4 number 18. No, probably 3 number 18 will be less than that. Check. I don't know.
It's 763.
So it's not good.
So 3H20 is perfect.
Yeah, but check 4 number 18. I don't know what you would get.
10,000.
1,000. So this is the best case.
This is the best one.
Yeah. The best case, because you cannot use 2. 2 reinforcement is not. Because when you keep in your mind, when you have distributed reinforcement in your section, whatever section you have, you will decrease the potential of getting crack in your concrete.
So you assume it once you have the AS.
When you have AS equal to 883,
Then you assume it.
then you assume a number of something. So 3 number 20, 4 number 80, 18, I don't know, 3 number, as you said, 3 number 25. Whichever is closer to that 883 is the best, because you need to pay for that, because the more you use reinforcement, the more you need to buy, the more you need to pay for that. So the more closest you get to that number, the better. All right? So now from this line, we are going to calculate the deformation and to see if the deformation is fine or not. Rho 0 was this formula, remember, in that slide? That's very straightforward. So this is rho 0. And the rho and rho 0 should be compared together to see which formula from those 2 we need to consider, right? The rho is the reinforcement ratio based on this number, not this number. Whatever you need. Rho is 883 over BD. Okay? D is this number minus 50 millimeter. Okay? So if rho is less than rho 0 or more than rho 0, why there exactly is, oh no, it's here. So it's 0.008, this is 0.006. So rho is more than rho 0, okay? Because of that, you need to use the second formula. Okay? I calculated rho and rho 0, and based on, I need to use one of these. Because rho is more than rho 0, I will use this one. Question?
Rho 0 comes from Eurocode. Calculate.
You tell me, rho 0 comes from this formula. FCK. You only need FCK, 40 megapascal. Put it here, you get this number.
So if it's greater, we use the second one, sorry, or?
No. The definition of rho, the definition of rho is the required tension reinforcement. Required, not what you put it there in practice. All right? Then rho is the required tension reinforcement you put there. You know what? Because if I put a 900 something, I'm unconservative. When I put more reinforcement, the deflection will be less. I want to use the less number here to have more deflection, to be conservative. Okay? Everyone good with this? We calculated rho and rho 0. Now we know that the second formula is the case we need to go for. So we have rho and rho 0. We need rho prime, which is 0. We are singly reinforced. We are singly reinforced. We don't have any compression reinforcement. Rho prime is always for compression reinforcement. Rho prime is the required compression reinforcement. It's 0. FCK we have 40 megapascal. K, we just got it from that table. We need F1, F2, and F3. That's it. All right? Okay. For simply supported, K is 1. All right? Although there are many parameters, but most of them are 1 or something. Yeah.
How would we reference a table like this?
What do you mean reference?
Say on a piece of work, how would we reference it?
It's table national annex number 5.
That's how you want us to reference.
Yeah. And you can see here, when the book, when it says, where's K?
EN
19
at the top.
Yeah, right at the top. EN 1992. There, just below stop.
No, that's the name of the book. That's
K is not mentioned, is it?
the book doesn't reference it here for some reason.
K is 1, national annex 5.
That's fine, like that.
Yeah. This is the common practice when you're working in a consultancy engineers and you're preparing a report for some clients, technical report. It's exactly the same thing you need to do if you want to show that you're calculating something. You need to reference, from National Annex 5, K is 1. So it means that you can just check the National Annex table number 5. You will see that K is 1.
So this is how we reference in our report as well, or do we use the Harvard style to reference?
The Harvard style is for reference section.
For the equations, we do this.
Through in the body of your report, if you're doing something, or in the Excel, you're calculating something, this is the proper way of referencing, okay? But the Harvard thing is something different. In each report, at the end, you have a reference section, okay? You will reference to books, to papers, to internet, to whatever. Even if you have used a pamphlet, you can reference it. In that section, you have different sort of configuration like Harvard referencing or APA referencing or Chicago referencing. So that's for reference section. This is when you are doing some calculation, right? In the body of your report. So when you say K equal to 1, you say from National Annex number 5. Right? That's why I told you this. I chose this book because the way of writing is like this. It's interconnected with the Eurocode and National Annex. And wherever you're chasing something, you can see, okay, why K is 1, go to National Annex number 5.
So when we're writing a report, you preferably want it in this style.
Yes, of course. And this is the professional way of calculating. Calculation sheets for civil engineers. And on the Moodle, you can find National Annex, you can find Eurocode, you can find everything. I've put everything there for you, you know. So, this is the formula we need to use, right? We have everything but F1, F1, 2, 3, right? F1, 2, 3. F1 is this formula. Again, it's coming from here. This is the Eurocode. This is F1, this is F2, this is F3. What are they? F1 is 500 divided by FYK, 40 megapascal. AS required 800 something. AS provided 900 something. These two values both contribute to F1. What you require, what you provided. Is it difficult? You have FYK, sorry, FYK, it's not 40. It's 500 megapascal. It's for steel. It's FYK 500, this one, megapascal. AS required 883. AS provided 943. You calculate F1, you will get 1.07, but always keep in your mind that F1 cannot exceed 1.5. If you calculate here and you get 1.6, you should say F1 is 1.5. Okay. It means that when you calculate F1, it should be always less than 1.5, not exceeding that. Usually it doesn't, you know? Usually it doesn't, but in any extreme case, if it happens to be more than 1.5, just take it 1.5. All right? Any question so far? No. F2, F3 are 1 because of, I will tell you, when they are not 1. But here, both of them are 1. F2 says, if you have a flange section means you have a beam like this. This is web, this is flange. So the thickness of the flange and beam are different, all right? If you have a flange section where the ratio of flange breadth to the rib breadth exceeds 3, then it's something. So it's not the case here. If you have a rectangular section, it's 1. It doesn't change anything. F3 is 1 again. What does it say? For beams and slabs other than flat slabs with spans exceeding 7 meters. It's an amplification factor, F3, when you have a very long beam. 7-meter beam is really a long beam. All right? And the deflection is really problematic. So that's an amplification for taking into account this matter. And the value will be 7 divided by L effective. If it's, which supports, there's even the expression, should be multiplied by, should be multiplied by 7 over L effective. Which is not the case here. Our beam is 6 meters. Usually beams are from 3, 4, 5, 6 meters. 7, 8 meters are very exceptional beams cases. They are not everywhere. And if you have very long spans like beams with 7 or 8 meters, usually we do not design those cases
with regular reinforced concrete design. Have you ever heard of pre-tensioning or post-tensioning cases? So when we have long spans, we usually use some particular technologies, which is pre-tensioning or post-tensioning, which I plan to dedicate 1 or 2 sessions of the term 2 to describe what are they and what kind of technology they use there. It's very interesting, amazingly interesting, how you can build a span of 10 meters, which you can never do with these kind of calculation. A span of 10-meter beam, for example, or slab, or even more. Sometimes, I don't know, 15 meters.
How do you calculate pre-tensioning and post-tensioning? Is it prescribed by Eurocode? Because I assume Eurocode is very old and it's a new technology. So
I haven't checked in Eurocode, but I think it is there. But if it's not there, it's okay. You can use some other codes like American code. Yeah, it's wherever it's silent. Wherever any code is silent, doesn't provide anything, you can use the other valid codes around the world. That's fine.
Confused for F1 equals 310 divided by stress S. That equals to 500.
Forget about this. Just use this one.
stress S is the bending stress of the beam or something?
No, that's sigma S is the ratio of these two over FYK.
Don't look at that.
No, just forget it, because this is what we need. The AS required, AS provided, FYK. We have these three. Right? So now we have F1, F2, and F3. All right? We have everything together. We have K. We can put everything together in this formula. Again, it doesn't work.
What's your title?
You can put all the values in this formula, and if you do so, you will get this number, 19.49. All right? You have all the parameters. If you run the numbers, you will get 19.49. It means that if your L effective over D, in your case, is less than this, you're fine. If it's not, you're not fine. How to calculate L over D for my case is 6 meter over D, 425. I deducted 50 millimeter from this for D, all right? This is the actual L over D for my case, which is 14.12, which is less than 19.49. Life is beautiful. Deflection is fine.
70.
Was it difficult?
70.
So you are sure that the deflection is in the range of acceptable deformation.
So that's thick.
That's thick, yeah. Absolutely, it's a thick. The beam is adequate with respect to deflection.
So if that was over, it wouldn't. If the beam was like, let's say 20, it wouldn't be.
Yes, it wouldn't be, yeah. You need to think of something.
Maximum length of the same beam could run up to 8,000 meters. To run the numbers, but if like 8,000 millimeters. But if it was 8,000, the thing would have changed, right?
Yeah,
Like
FF2
would
and
have changed. And then again we are into a problem. So we have to again change F2 and check the number.
Yeah. But sometimes you can elaborate a little bit with the formulas. For example, if this is 19.49 and for some reason I will get 19.52 here, for example, very close, but a little bit more than this. Something like you asked, right? I get here 19.52, which is more than this, but really very small value. If you increase a little bit this one, AS provided, just to use, instead of 3H20, use 4H18 to get 1,000, like instead of 900. You will increase a little bit F1 and a little bit this one. So you will be fine.
That's something you can discuss.
Yeah, yeah, absolutely. If you're very close, but if you're not very close and you're far away from acceptable ratio, you definitely need to increase the H.
So you're saying that mistakes are good sometimes?
No, I'm not saying that. This is not a mistake. This is a design trick.
Not a mistake. Alteration. Alteration.
Yeah.
Alteration.
Yeah. But if the difference is too much, you probably really need to increase the H.
Yeah.
The H of the section.
If it's the H.
The height of the section. There is no way other way. Or use a better concrete, a more strength concrete.
All that, yeah. It's good to make good notes for the exams. Too hard.
The main thing is I can't bullet point where I've gone too far.
Oh yeah, it's open book, isn't it?
Hope this is an exam question.
See question.
We decided to use F2 and F3 annex, and we decided if it complies to R1 or not.
Pardon?
If it complies to our given information.
Everything.
So that if it goes over L2 will use something else.
Still not really different.
Yeah.
Something like that.
Yeah, F2 it's only valid if you have a flange section, which you don't.
And how do you know if you don't? The flange section.
It's like I-beam or something.
I-beam.
No, it's just the same thing.
Flange is. This is a flange.
What would it equal if it was a flange?
Huh?
What would it equal?
0.8, I guess.
0.8.
It said.
If it's a flange, it's
Yes, I saw 0.8. Yeah.
0.8. Yeah.
L will be.
That's the only type. So if it's not 1, it's 0.8.
No, it's not.
It should be multiplied by 0.8.
What do you mean?
That means F2 would equal
So
0.8.
it's this one.
That would be, that's the expression, right? So that's the whole expression.
Yeah. No, I have to exactly think what I'm to do.
If it exceeds 3, the values of LD given by expression 716 should be multiplied by 0.8. Yeah, that's F2. This is F2.
So it's not.
If it's a flange. And if the ratio of these exceeds 3, otherwise it's 1. 1 means it doesn't contribute to anything, it's just 1.
And if the L is exceeding 7 meters,
Yeah.
it is.
It will be 7 divided by L effective.
Like
No, it's just.
5 centimeters. What is 5 centimeters?
What is our L effective?
50.
L effective is the length of the beam minus 2 supports. From the support to support, the edge of those supports. You know, if it's on the wall or column, the edge of this support to edge of this support. Not from axe to axe.
This is like a kind of.
But if
It's not infinite. Have you not seen it?
Most likely.
it's not okay. No, just
We provided the width support if that's the case.
Here and here.
Here
and here. Yeah.
Here.
Here.
This.
Yes, and so this and the whole.
You know, you're engineers. If there is a question in practice, if it's provided the edge of the support, okay, you use it. Otherwise, if it's not known, think of, okay, this is a structure, I assume something for that. You know? In the design area, everything is not clear. You say, okay, probably I will have some columns of 40 centimeters, or two walls of 40 centimeters. So 20 centimeter, 20 centimeter, and should be deducted.
Are you doing
You're
it?
engineer, you know? You should assume rational decisions in different places. It's not, in the real world, it's not like everything is provided for you. You just put the numbers in the formula to get the answer. You are an engineer. You should think of rational conditions that will occur in real world. So it's not provided. Nobody knows what kind of. I can assume something.
In my calculations,
Change the thickness by 10 centimeter. It will not change all of my design, does it? It's just probably will affect the second precision of your calculation. You know?
That's why I'm doing it.
Because you have time.
We don't
see how nice my
Oh, yeah. You should actually use a scanner for that.
Oh yeah. We do on the app.
It's a very hot discussion.
What do you want to see?
Yeah, exactly.
Very hot discussion over here.
Yeah, about the coursework. We're going through it.
Good. The more we approach to the end of the term, the more active students are. And, you know, the more crowded the university is. You see everybody running from it. This coursework. No, go to that one.
Yeah, so many
that's why I put a coursework for, not for you, for again for you for term 2, for final and master students. I put a coursework at the middle of the term. So from the middle of the term, they are running. And then for the next term of you, I didn't put for this term because you had constructionarian. For the next term of you have in the middle and in the end. So after January, you need to run. Yeah, one course.
It's just one thing which we
The
have
name is
decided.
one course, but split it in different parts.
Now we design the section, then we design the length and the deflection, I guess, and then we design the slab or something.
Wow, nice.
Something.
It's the
Are you
same
sure?
thing,
No,
but
this stuff is just elements.
better than doing all it.
Only this year's.
Però era tipo il 2.
So this example 613 was, as you see, was not very difficult. It's singular reinforcement. All right. The next example is exactly this one, but they just increase the external force to be double reinforcement. That's only the difference. Nothing changes. Instead of the second formula, you're using the first formula, I guess, if I remember. Nothing different. Yeah, until here, it's the design for reinforcement. So you have this one for I don't know. This is AS. This is AS, A prime S. It means that tension and compression. You have two set of reinforcement. If you have forgotten about singly and doubly, just go to the previous sessions. And here, the only difference is you have rho prime. The rho prime was 0 in the previous case because you didn't have any top reinforcement, did you? So now you have compression reinforcement. You have rho prime. Rho prime is non-zero, right? The rest of the problem is the same. The rest of the problem is really the same. We calculate rho 0, rho prime. So it's more than this. Again, you are using the second formula, but you have rho prime in place. Okay, so the formula is here. You put F1, this time is 1.09. It was 1.07 in the previous case. And K is this one in this time. And we have rho prime here, F2, 1, again 1. And if you run the numbers, you will come up with this value, 6.42. Okay? And the actual L over D is 7.06. And oh, sorry, another thing is it changed the problem not to be a simply supported beam. It's the same beam but cantilever. One fixed and one free. Right? Cantilever always a problem because you know what does cantilever mean? It means balcony. When you're in a balcony, it's a cantilever, right? Connected to the structure, but underneath is nothing, right? So cantilever is important when you design a balcony. So everything is the same, but it changes to the cantilever. That's why K is different, 0.4. It's for cantilever. So the L over D is 7.306. And whatever you get from the formula is 6.42, which is not acceptable. Obviously not acceptable. And the length of balcony is 3 meters. Have you ever noticed how long the balconies are? When you go to the balcony, is it 3 meters? No.
1.5 meters. 1 meter.
Usually it's less than 1.2 meters. Usually. I don't say you cannot design a balcony of 3 meters with pre-tension, post-tension, or if you design, this is your structure. If you design a balcony for 3 meters, you cannot make it fine. If you increase H, you will come up with this fact that, okay, you need to have a section like this to be able, you cannot construct that section. Whatever in practice, if the architecture allows you, you can have element here like this, a truss element like this, just to have a support from beneath. And that makes, I mean, there are 2 elements because there's another one. So if it is a balcony, you can have more than 1, 2, or even 3. If you make a support from the bottom, yeah, you can design it. But
they normally wouldn't let that, would they?
Pardon me?
They wouldn't let that because there's someone underneath it with a power.
It doesn't need to go to the underneath. It can go to it can go like this. This is the story. This is the balcony. This is the window. It can go like this.
Yeah, so they wouldn't notice it.
Yeah, if they allow. If they allow.
It wouldn't be covering that view.
Yeah, there are some ways to do so, but there are other solutions like pre-tensioning, post-tensioning, etc. But without this kind of support or without modern technologies, usually you cannot design a balcony with a length of more than 1.2 meters. 3 meter balcony design is really very difficult to do. That's why the deformation is not okay. And when you do the beautiful of the design is when you do some practice in real world design, you get some feelings, you know. If a client comes to you and say, okay, I want a balcony for 3 meters, if you have the experience, you will say, probably it's not possible. Let's talk about with the neighbors if they allow to do some extra elements, you know. Otherwise, it's very difficult to comply with a 3 meter balcony. And the last example is about slab, I think.
Sure, where we went, I got this.
Or verify the suitability of the slab given a section 654. This is a slab that we worked with previously with respect to deflection between A and B. So it was a slab which had a cantilever as well, if you remember. So in that case, if you go to this example, you will see that there was a design like this. AS required was 508, provided was 523. And it was a slab sitting on two walls, if you remember. It was a slab and it had a continuous cantilever as well. So, what's the new point here? Nothing. Just F1 is something similar here. Row 0. The same procedure, K is 1, row prime 0, F2, F3.
Just repeat it.
But we just use K.
Let me just see. There is another point. When this formula gives you something like this, 79, there is a condition that it should be less than 40K as well. Here in this example, 40K governs. Let's see, in the previous slide, it was somewhere. 40K, it's here. Yeah, it's here. When Eurocode provides these two formulas, it says whatever these two give you, still it should be less than 40K. All right? The third case is the point is this one. Okay? So when we come to the last example here, when we use the formula, we get 79 point something, but 40K is, because K is 1 is 40. You don't need to comply with, actually it's vice versa. You should go for 40 instead of 79. So the actual L over D for this slab is 19, which is less than 40, obviously with less than 79, so you are fine. But there are 2 points. First of all, the reader should verify the deflection at the end of the cantilever in the slab as well. Because it was, if you take a look at this example, it was a slab sitting on 2 walls and continuing as a cantilever. All right. This calculation is only for the span between the 2 walls, which was 5 meters. Yeah, 5 meters. But you should repeat this as an exercise for you for the cantilever, like the previous one, to see if it's okay for the cantilever or not. I think the cantilever was 1 meter or 1 meter something. Probably it would be fine, right? And the second point is that if, this is not the case here, but if you calculate L over D, for some reason, you will come up with some number like 50, okay? You cannot say 50 is less than this one, so okay. That's why this condition is here. If you get 50, you cannot compare it with this. When it's more than 40K, the criterion is 40K, not this one. The lesser is governing your design. It should be less than 40. This formula in this case is nonsense. Or in other terms, the formula is nonsense when it gives you more than 40K. 40K is governing. All right? That's the whole thing for the deformation control. And usually in conventional cases of design, when we design for forces, deformations are fine, usually. But when there are some particular cases like long spans, like long cantilevers, the deformation will govern. And you should, anyway, you should check the deformation, but you can expect that for long span beams or for long lengths cantilevers, you will be in problem when you check the deflection control. And to solve that, of course, you should increase the stiffness of your element, or you can use modern technologies like pre-tension or post-tension systems. We'll talk about it next term for sure. Any question?
Not regarding this, but the shear slides, like the shear design slides are not uploaded on the Moodle.
Oh,
The shear slides.
Yeah, the shear design slides.
The video is.
The video is there, but the slides are not.
I will upload it. Okay. Thank you. Anything from health and safety?
No.
I got a question for you.
Yeah.
It's not about future.
All right. So if there is not any question, see you next week.
Thank you, sir.
I have a quick question about
Let's go then, yeah.
Here. Today we're like.
You hear you.
I don't like that. Well, you know why? I think the introduction was not bad. Should have been great.
I don't know.
You just thought it was the thing. We're like, what's the best thing? I came up with the last year. So many things. Why?
Hamza, remember Arkika saying during his last meeting that we have a presentation due on 6th of December.
Oh yeah. I know.
It was there on the presentation. Yeah.
Everything.
Sunday.
Oh yeah. I got scared. I'm not gonna do it.
How are you doing, brother? You are very good.
Where do you upload the presentation? Is there anything on Moodle? No.
I did.
If that's the case.
That wasn't me. That was someone else. It was someone else.
I just haven't been
The different. Yes, it didn't say it.
Reference in the culture. I need to reference everything. Like, okay, I got
I was on
the moments, in it, moments of that. So, equations that you found. I'm going to take a picture of it and then just reference it wherever.
See, Ricardo.
tag like he did.
Because the house.
No, I know. I'm going to take a picture of this, put it into my words for my assignment.
You put the
I'm going to do that.
less than 12.
Yeah.
Last question. Last question for you.
What does that mean?
Have these here.
They're gonna tell the government everything. Capito? Questo io non l'ho fatto. Dovevo farlo.
You don't have a staff here.
No, basically, this is around the free group to ask.
She also told me.
So a minute. It's alright.
Please do me a favor.
That's fine.
You're gonna make out.
Walls and the loading gate.
These columns will have
One.
double lengths of
Bye bye.
unsupported
I'm
lengths.
going home.
Oh, we got, oh, okay.
I'm not attending that.
You know, this is ground.
Who else am I?
This is column.
You're going home. I'm
Hello.
Oh, Laura is not here. Bye.
We need to ask you about
Yeah, no, I'm gonna go live.
Your probably your
You want chicken
columns
and beef in one night? You can't.
Sorry, sir.
You felt I thought you double check. Thank you, sir.
Who's your
What would you recommend it?
Simon?
Ali Reza's one. I'm still going through. I'm not finished.
That guy.
I've only done
What chart as well? What thing did you get?
What did you give it?
What did you get?
Referencing as well. Yeah, there's more references than you.
What did she mark you as?
They are very.
I think she gave you 1.5, but she rounded it to 2. But she gave me 2.5 and rounded it to 3.
Wait, who's your thingy?
Colin.
What actually happens?
Colin?
What actually happens?
I
think he gave everyone two.
No. Colin gave.
Got 4. That's.
I mean, that's a pass.
So I want to all your
I'm scared now.
I would expect if
Oh, but this is the thing.
No, it's.
You are 4 marks away from somebody else.
Fucking bitch. She said I'm speaking. No, it's
design them.
6%.
Design them if it's not okay for them.
40% is
Everything.
6 marks.
same.
See?
I was thinking, what's pull?
Don't worry about the point. As long as you pass, everything is obviously.
There will be some forces.
90%.
Yeah, the main thing is that the actual location.
I did, but is that?
You finished your previous thingy.